closed. Let's take a look up here. I'll let you guys get some work done though too today. So where we left off yesterday, we were looking at clearing fractions, right? Remember we said that when we're clearing fractions, you can distribute through by the least common multiple of the denominators, but that only works if you have a sum of terms on both sides, right? So you have to get to that stage first before you can clear fractions. So the problem here, right, was on the right side, we have a sum of terms, but on the left side, we have a product. We have this 1/2 that's being multiplied by this quantity. Everybody see that? So we can't do it yet. First, we have to distribute the 1/2 to the left side. And let's see, I just multiply straight across, and that gave us what? 7 over 16x and minus 3/8 equals 13/10 x minus 1/2. And now we can go ahead and proceed with clearing fractions, right? So we'd have to find the least common denominator of all of our denominators in the blue equation, right? 16, 8, 10, and 2. And we figured out that was 80, right? We could just do multiples of 16 until you find a multiple of 16 that's divisible by 8, 10, and 2. And the first one you'd get would be 80, okay? So now let's finish this process. When we multiply through and we're clearing fractions, remember that instead of multiplying first and then reducing an enormous fraction, we're going to be smart and switch the order around of the operations we do. We're going to reduce first and then multiply that by the numerator. Much, much easier. So 80 over 16 reduced to 5. 5 times 7 is 35 times x is 35x, right? 80 over 8 is 10. So 10 times 3 gives us our 30, so minus 30, equals, what about the other side? 80 over 10 would reduce to what? 8. Okay, so, oops, didn't want to do that. What'd I do? Oh my goodness. There we go. So, what did we say? 80 over 10 reduces to 8. Multiply that by the numerator. What's 8 times 13? Quick, quick, quick. What is it though? Mental math's good for your brain. It helps you do 104. There you go. So I get 104x. If you look at a real-time PET scan of a person doing mental math, it's the very same parts of your brain that are active when you do algebra. So doing mental math actually makes you better at algebra. 80 over 2 reduces to 40 times negative 1 is minus 40. We won't even finish. From there, it's a piece of cake, right? No big deal. We push the x's to the right side and isolate the x. No big deal. Okay? All right. How many we got here? 3, 6, 9, 12. So 18. We could go, how about 2 per board? Why don't you work in teams of 2? Go to a board and try that one out. There should be pens on the, if you need more pens, I think there might be some in that box over there, but I think there's a bunch of pens already around the room. All right. So again, right, you got to, before you jump into these things, the further you get along in math, the more it pays to pause for a second before you jump into problems. Because at some point, they start to get complicated enough that if you just jump right in, you're likely to take a wrong path, and it might be hours later before you realize it, right? At some level. So we're not quite at that level yet, but it gets there in a hurry. So you got to think about this. Well, okay, this is no big deal. We're just isolating a variable, but we have to distribute this fraction because we don't have just a sum of terms on both sides. We have to have that before we clear fractions. So first step, and I think everybody did this, was to distribute that through, right? Okay, let's talk our way through that. So what's that going to give us when we distribute the negative 15/16? What about here? 15 over 5 reduces to what? 3. Okay, so that reduces to 3 over 1. So I have a negative, and I'm going to get a 3 over 1 times 4 over 16 reduces to what? 1 over 4, right? See how we did that? So we kind of, let me color code this a little bit. So here's what we did. We took that product, right? Because remember, we can multiply things in any order we want to. So we could have easily exchanged the 15 and the 4 there, right? When I distribute. So the 15 goes with the 5 and the 4 goes with the 16. Just a little trick. I mean, you don't have to do it that way. But then we end up with a negative 3 over 1, and then this becomes, this becomes 1 over 4. So just an easier way to get that fraction maybe. Now what about when I distribute over here? Okay, so now I could regroup this one also, right? I got a minus sign when I distribute the negative, and I could do the 15 over the 3 reduces to a 5 over 1, right? And the 32 over 16 reduces to a 2 over 1. Everybody see that? Okay, and you can probably do that in your head. And that sounds weird for a math teacher to say that, but with a high level class like this, you guys can start to do that stuff. But it takes a little bit of practice. I would urge you not to necessarily write down every individual little step at this level. It's just too much writing and it breaks your train of thought. I mean, start to power through some stuff mentally a little bit too. And again, just it trains your brain. It's like lifting weights with your brain when you do that. So what do we get then? We get negative 16 equals, yeah, if I multiply straight across, I get negative 3/4. And there was a variable there too, wasn't there? Yeah, there's a q, it looks like. So we get a negative 3/4 q minus 10. Okay, now here's where people took a couple different paths, and both of them are okay in this case. You know, you could just distribute a 4 through and clear all the fractions. That's fine to do, and that's honestly, that's probably what I sort of intended you to do. But some people noticed here that because you've only got this one variable and this one fraction, you could also just push the 10 to the other side and divide each side through by negative 3/4, right? Everybody see that? So we could have just added 10 to both sides. And that's giving us, that's giving us negative 6 equals negative 3/4 q. And now rather than multiplying by 4, why don't we just multiply by the reciprocal? There is one other tricky thing we could do here to make this a tiny bit simpler. If I have negative something equals negative something, what could I do to both sides? Good, I could distribute a negative through both sides and change the signs, right? That might be useful. So we could do this. We could make both of those into positives then. And now it's a little bit easier because I could multiply each side through by 4/3. Right? If I distribute that through, 4/3 times 3/4 is giving me 1q, and 4/3 times 6 over 1. What's that going to give me? I'm going to get 8, aren't I? I'm going to get 24 over 3, because 6 is the same as 6 over 1. Everybody agree? So I'm 24 over 3 is just 8, and there it is. Okay. Okay, good stuff. All right. Okay, next issue. So this is easier. Really, that last topic, clearing fractions, I think is a little bit tougher than this. Proportions are simple. What's a proportion? A proportion is an equation where I have one fraction equal to one fraction. That's it. There's nothing else, no other terms. One term equal to one term, and each term is a fraction. Okay. When you're solving proportions, rather than going through the whole process of clearing fractions, and you can do that, but what it all boils down to, it's the same thing as just cross multiplying. Okay, so you can take a big shortcut here. When you have a proportion, you can say that that cross product, A times D, is equal to that cross product, B times C. Okay, so let's try this example. Everybody agrees that's a fraction equal to a fraction, right? So let's look at this cross product. What is 5 times the quantity x plus 4? Well, let's write it that way. There you go, 5x. It's going to be 5x plus 20. Whoops, right? You got me thinking ahead here. It's going to be 5x plus 20, isn't it? So there's the red cross product. Here's the blue cross product. 2 times 3 is just 6. And so that's an easy equation now, isn't it? Distribute the 5 and solve for x, and it's a piece of cake, right? We won't even go there. We don't even have to do that. You guys can all do that part. What I want you to see is setting up that simple equation is just cross multiplying. How about something like that? So now it's not a hard problem, but they're asking you to do a process here. So take a second and think about what they're asking first of all. There's a lot of the terminology we've been using over the last few days. Say it again. No. So let's read through this. What does this part mean? Evaluate z squared plus 3z. You would, right? So we're going to evaluate means value means number. We're going to plug a number in for z for this expression for the value of z satisfying this equation. Well, what does that mean? The value of z satisfying this equation. That's just, I'm just solving for z, aren't I? Right? I'm going to find the value of z that makes this true. So here's a proportion. We would just cross multiply to solve this. So we get the red cross product, 3 times the quantity z minus 4. Now, I haven't seen you guys do a bunch of board work on this yet, but if you're anything like my Algebra 2 classes, that I've watched all day doing other stuff, people get real lazy about forgetting parentheses. Does everybody see why we need those parentheses? If I just said 3 times z minus 4, what's wrong with that? Yeah, I'm just only multiplying the 3 by the z there. We have to have 3 times that whole quantity, don't we? Okay, so that's equal to the blue cross product, which would be 2 times the quantity 2z minus 7. And now we do have to solve this one to do part B, don't we? So if we distribute here, what do we get when I do the red distribution? 3z minus 12 equals blue distribution. Where am I pushing the z's? To the right. Good. So we're going that way. So those guys cancel, and I end up with negative 12 equals z minus 14. So what's z? 2. So now for part A, what do I do with that 2? Plug it in. I'm plugging it in for each of those z's, right? And so what do we end up getting? 2 squared plus 3 times 2. So what? 4 plus 6 is, there we go. Give me 1 to 5. How are we doing? Does that all make sense? Okay. Okay. Any questions on that last one? No? Okay. Okay, some special cases now. So what if we're solving equations? Let's look at this one. So this isn't very hard, right? We've got to do a little simplification. I can't point to a single c, so I have to simplify things. What do I need to do first to simplify? Distribute the 5. So I end up with 1 plus 3c equals 5 minus 5c plus 8c. Well, I could combine some like terms on the right side. What's negative 5c plus 8c? 3c. So I get 1 plus 3c equals 5 plus 3c. Now what? Ooh, something weird happened. If now the next step would normally be to push the c's to one side or the other, right? But in this case, when I subtract 3c from both sides, look what happens. We end up with the answer 1 equals 5. Okay, is that true? What is it? Okay, good. So you guys already know this means no solution, doesn't it, right? If we start with an equation and all the variables disappear and we get a false statement, that means that it is never true. There's no value of the variable that could ever satisfy this equation, and so there is no solution. Say it again. Okay, so it's the empty set. Yeah, if you wanted to, you could write that as no solution as the empty set. So the terminology that goes with that, we would say that that is an inconsistent equation, right? It's inconsistent because there is no way to ever get a value of the variable that's going to make it true. Okay, so when you do the assignment and you're looking at examples where you're looking at special cases, this would be labeled inconsistent, an inconsistent equation. Okay, let's look at another weird example. What about? Oops, I think I need to go. What about one like that? Okay, so if I do the math here, and we can just kind of zip through this. If I distribute the -8, I get 40 minus 8x equals -8x plus 40. So I could add 8x to both sides, everybody agree, and the x terms are just going to drop out. And look what happens. We end up with the answer 40 equals 40. That's true. What does that mean? Infinite solutions, right? It means every possible value of x is going to work here, right? So it's infinite solutions, and the term we use to describe that equation is that's an identity. If an equation works for all values of a variable, we call it an identity. Okay, just some vocabulary. And then, okay, all the other cases, every other example that we've looked at where we got a single solution, that's what we call a dependent. I'll make a note of that. Whoops. If you have one solution, then that's a dependent equation. Okay, just some vocabulary words. Okay, and we'll close up. When are we out of here? Okay, so the last thing we'll look at for today, and then I'll give you some, tomorrow you get a little work time. Last thing we look at today are what's called literal equations. This is no big deal. These are honestly, people make these out to be really hard, but they're no harder than anything you've done, right? You use the same algebra steps. The only difference is instead of having a single variable and a bunch of numbers, this time we're having a bunch of different variables. Like this would be if you're solving a formula for a single variable. Like let's look at a couple quick examples. Like how about this guy? What if I have this formula or this equation and we want to solve that for v? The same rules apply that applied when we were solving equations earlier where we had a single type of variable. First of all, can we point to a single v? Because that's what we're solving for. We can, right? There's a single v right there. So if I can point to a single v, now I can just use inverse operations to isolate that v, right? So let's write them down. We're using our PEMDAS tree, and we're isolating. We're using inverse operations. Okay, so what's the first thing we have to do here? Is there anything? Now notice that we don't get to parentheses until the last step, right? So when we talk about addition or subtraction or multiplication or division, we're talking about these operations outside of parentheses because we don't get to the parentheses until the last step. So outside of the parentheses, is there any addition or subtraction we need to do to both sides to isolate that v? Outside of parentheses. I don't see anything, do you? That would be like if we had an additional +3 over here or something. Then we'd subtract 3 from both sides, right? Remember, every step of isolating, of inverse operations, should do something useful. It should cross something out. So we don't have any of that yet. Is there any multiplication or division outside of parentheses? Yeah, there is. Look, there is. we're multiplying by 1/2. We want to undo multiplying by 1/2. How do we do that? Multiply by 2. Right, we don't divide by fractions. Instead of dividing by 1/2, we always multiply by the reciprocal, right? So the first thing we do is multiply each side through by 2/1, same as 2, right? The 2/1 cancels the 1/2, okay? Could you have distributed the 1/2 first? You could have, but this is better. This takes fewer steps, right? They both would work. So what are we left with then? At that step, we're left with 2 times 7W is 14W. On this side, we just have W plus V. So finally we get up, there's no exponents. We get up to the parentheses, and what's, now we can get rid of them because they're by themselves. What's the only thing we have to do in parentheses, that last step, to get the V by itself? Subtract W. And so we get V equals 13W. There you go. We isolated V. Now we're getting other variables in our answer, but that's to be expected, right? Because we have other variables in the original equation. Let's try one more of these. How about this one? We're going to solve for B. Can we point to a single B? We can, right? So now what's the first thing we need to do here? Remember, we've got a fraction bar, so everything in the top is a quantity and everything in the bottom is a quantity. You would, right? The first thing we would do is we're undoing division. How come we're not undoing addition? Because the addition is inside parentheses, right? There are implied parentheses around the numerator. So even though we don't write them, they're there, right? So step 1 is to multiply each side by C. So there's step 1. And that cancels the C's, right? And then we get A plus B equals 5C. Last step to solve for B, subtract A. And that comes up here in parentheses. So those guys cancel, and we get the B by itself equals 5C minus A. Okay, again, we'll get C's and A's in our answer, but that's to be expected, right? We still got the B by itself. Okay, we'll look at that one tomorrow. We're out here in 1 minute, right? Okay. Oh, no. How many? Oh, we're good then. Thank you. All right. So what about this guy? This is a little more challenging. We're going to solve for H. Okay. But what could we do here? Anybody have a suggestion of what we could do here to maybe make this whole thing a little bit easier? Yeah, we could clear the fractions, right? Let's multiply by 3. Let's make everything a little bit easier. Do you have to do that? No, but it makes life easier. So if I distribute the 3 all the way through, what am I going to get? Well, I get 3V. Everybody agree the 3's are going to cancel there, right? So I'm just left with 4 pi HR squared plus the 3's cancel, and I get 2 pi R cubed. So now we can point to a single H. What are the steps going to be to get that H by itself? So we got to do inverse operations. Well, over 3 though, right? When I distribute the 3's are going to cancel. Okay, makes sense? So what's first thing then? Is there any addition or subtraction I have to do to get that H by itself? Yeah, there is, isn't there? Look, the H is buried in this term, but I've got this whole other term that's being added to the H term. So I got to subtract that term. I'm subtracting that whole term from both sides. So step 1 is subtract 2 pi R cubed from both sides. And that's good because It cancels. I get to cross something off, right? Every term of inverse operations, I should get to do something productive and cross something out. So now what? I've got 3v minus 2 pi r cubed equals 4 pi h r squared. Okay. Multiply, divide. Is there anything I should multiply or divide both sides by? I could divide both sides by, say it again. By what? Division is what undoes multiplication, right? Right now that h is being multiplied by stuff. How do I undo multiplying by stuff? Divide by stuff, right? And I can do them all in one step. Step 2, I could divide both sides by all the stuff that's being multiplied by h, right? 4 pi r squared. And that's good because the 4, the pi, and the r squared all cancel, leaving me with just my h, which is my goal. So I get h is equal to, and then over here, I can just leave it like that. That's fine. It looks really ugly, but that's okay. It looks like this is the expression that h is equal to. 3v minus 2 pi r cubed over 4 pi r squared. Now, why would we do this stuff? Well, let's just assume maybe that in this case right here, this is the volume of some weird shape that has a height and a radius to this shape, some kind of weird cylinder or something, right? So right now, this is a formula for volume because it's equal to volume. Everybody agree I could calculate the volume by plugging in whatever the height and the radius are. I could plug those values in and get a number for volume, right? What if I wanted to rearrange that formula and write the formula for height, where I'm going to input volume and radius? Okay, isn't that what I just did here? I just created a new formula that predicts the height by inputting values for v and r. Okay, so like another example would be if you wanted, we have a formula for calculating the temperature in Fahrenheit based on degrees Celsius. So I could input a temperature in Celsius and it would calculate Fahrenheit temperature. What if I wanted to flip that around? Well, then instead of isolating the F for Fahrenheit, I'd have to isolate the C for Celsius, right? And I'd have C equals some equation involving Fahrenheit, right? So we do this all the time in science, where we want to rearrange a formula to make it useful for whatever we're trying to do, okay? Okay, last one. We're out here at 45, right? Okay, yeah, this will be the last one. So what are you going to do here? Yikes. How am I going to solve that for R? What do you mean by that? So like flip each of those? I can't do that though, and here's an easy way to prove it to yourself. What if I did something like let's try it with just numbers. And this, you can always do this kind of thing. Like, would you agree that 1/2 plus 1/4 equals 3/4? Everybody agree? What if I just flipped everything? That would give me 2/1 plus 4/1 equals 4/3, but that's clearly not true, right? So I can't do that. There's a case where it didn't work, so we can't assume it's going to work for any other case, okay? Ideas. That's a challenging one. Say it again. Yeah, you might. You might. What do you mean by that? Times stuff by 1 in what form? Well, okay, so this, I think you're alluding to something like when you add fractions up, you always multiply by 1 to get common denominators. Got an idea? multiply. Okay, but if I can't, the problem is, here's my equal sign, and when I'm doing equations, when I'm solving equations, I have to treat both sides of the equation equally. So I can't just multiply one term by something. I have to do something to the entire left side and the entire right side. Okay. What could I do? Yeah, eventually, yeah. Okay, now let's think about this. This is really a tricky one. I mean, this is a pretty hard problem to come up with something. But we were clearing fractions at the beginning of the class, and think how when we cleared these fractions, what we did, right? We multiplied both sides. Let's pick like this one. We multiplied both sides through by the least common multiple of all the denominators, the smallest number that all the denominators divided into, which was 80 in this case, right? Well, we don't have numbers for our denominators and we're way up there, aren't we? For this guy, we have variables. But what's the smallest product that A and W and R would all divide into? Say it again. AWR, right? A times W times R. Agreed? Because, like, for example, what if I do that? What if I multiply through, distribute through the whole thing, A times W times R, which I could just write as AWR. I don't have to put the times sign there, right? I mean, that's things together next to each other being multiplied. When I distribute that through, look what's going to happen. When I distribute to that term, this is all over 1, so I'm going to get AWR over A. Well, what happens to the A's? They cancel, don't they, right? Because they're factors. They're things that are being multiplied on the top and the bottom. You can cancel like factors in fractions. So those guys would cancel. When I distribute to the 1 over W, I get A times W times R over W. Look, the W's cancel, right? What about over here? A times W times R over R. The R's cancel, right? It's looking a lot better, isn't it? We don't have fractions anymore. Now we have WR plus AR equals AW. Now, this is a challenge problem. I wouldn't give you one like this on the assignment because this is pretty tough. What would the next step be? If I'm solving for R, these are not like terms, are they? I can't combine those terms like I could with numbers. But we're looking way ahead here. We're looking ahead probably about 2 units right now, but you've done some of this before. WR plus AR, is there anything I could undistribute from those two terms? An R. Yeah, I could that's called factoring, right? We'll review factoring later. We're gonna factor out an R, which means we're gonna undistribute an R. And what's left behind if I undistribute an R? W plus A, right? Equals AW. Okay, we're almost there. What's the last step? What's the only thing I have to do to get that R by itself? I got to divide by whatever's being multiplied by R. I've got R times this quantity. To undo multiplying, I divide, right? So I could divide each side through by the quantity W plus A, and I got it. Okay, that's a pretty challenging one, right? You too.